Hello, everyone. My name is Kang Wen, and I'm an associate professor at Zhejiang University. So today it's my great pleasure to present our work, Parallel VLM. The first author of this paper is a third-year PhD student in my group who is working very hard in the past few months to get this work published. So first of all, let me give a brief introduction of the background of our work. So with the rapid advancement of large language models, they have already achieved powerful capabilities in long-form video understanding. However, LLMs adopt strict autoregressive generation paradigm, which inherently bring serious decoding bottlenecks. For video data, this problem becomes even worse, as it usually contains extremely long token sequences, which would lead to increased single token generation latency. So specifically, the figure on the left illustrates the architecture of Lava 1 Vision. Each video frame is encoded into 196 visual tokens, so processing 128 frames will result in an ultra-long sequence of nearly 25K tokens. The right curve clearly demonstrates that the single decoding latency would scale linearly or would increase linearly as the number of pre-filled video token increases. To accelerate decoding process of large vision language models, existing acceleration methods can be mainly categorized into two directions. So the first direction is visual token pruning. This method eliminates redundant visual tokens to reduce computation overhead. A representative work is FastV, which achieves under 2 times speedup. However, this scheme inevitably causes information loss in output distribution, and its acceleration effect is limited by full parameter forward propagation. The second direction is speculative decoding. SpecVLM is a typical representative, which follows the classic draft then verify paradigm and realizes up to 2.6 times speedup. So even so, its acceleration performance is largely constrained by the mutual waiting time between the draft and verification procedure. So there is still a mutual waiting bubble between the draft and the target model. So our proposed parallel VLM falls into the speculative decoding family. So by designing parallel pipeline and unbiased alignment mechanism, which we merge these two kind of techniques, we would completely eliminate the mutual waiting issue. Without any information loss, our method would achieve a great speed up. All right, so before we introduce our core method, let's briefly review the fundamental knowledge of speculative decoding. So let me give you a quick crash course of the speedups, the theory of speedups in speculative decoding. So the vanilla speculative decoding would strictly follow the draft then verify workflow. The small draft model first generates multiple candidate tokens, and then all generated tokens are verified sequentially by the large target model, which directly causes a mutual waiting problem, as I said. To solve this issue, the parallel speculative decoding, which is also called PSD, is proposed recently. We also have another paper published in iClear earlier this year, which is also on parallel speculative decoding architecture. So this architecture is proposed recently with an innovative draft and verify framework. So in this design, the draft generation and target model verification proceed simultaneously, which fundamentally removes the mutual waiting bottleneck and would greatly improve the pipeline utilization. So there are two core mechanisms determining the final acceleration efficiency of speculative decoding. The first one is the speedup ratio between the draft and the target model, which is denoted by the C here. All right. So the second one is the average token acceptance rate tau, which is denoted by the red letter tau here. As shown in the formula on the right, on these formulas, a larger speed-up ratio C means faster token drafting and more token being verified within the unit time, right? When meanwhile, a higher acceptance rate would indicate that more candidate tokens can be directly confirmed by the target model. So, although speculative decoding shows great potential to speed up, right? Directly applying the vanilla scheme to video large language models, to video large vision language models would still face critical defects, which is exactly how it motivates our research. So first, the verification window size is severely limited. To maximize parallel efficiency, the optimal verification window is highly dependent on the model speed-up ratio C. So larger window size can significantly boost verification efficiency, while in real video model scenarios, the practical speed-up ratio is only between 3 to 5. For example, the ratio is 3 for 7B draft model paired with 32B target model, and 5 for 7B paired with 72B models. The second, serious cross-model alignment degradation would occur, which means that the output from the draft model was rejected, will be rejected by the target model. This means misalignments. Right? So most of those training-free speculative decoding method would have a weak inherent feature alignment between the draft model and the target model because the capacity of the target draft model is limited. Under the ultra-long sequence setting of video understanding task, the alignment degree would drop sharply. The essential reason lies in huge video content understanding gap after modality fusion between small lightweight model and large powerful models. So in general, there exists an inevitable trade-off dilemma between the verification window size and the cross-model alignment. So we can expand parallel verification window gamma by pruning visual tokens inside the draft model. However, excessive token pruning would reduce effective video feature information carried by the small draft model, which would further widening this gap, right, between the small and the large model. So we can see that there is a gap between speed up and the acceptance ratio, which we can use pruning as a proxy to strike a balance between this potential trade-off. So the declined token acceptance rate will finally offset all efficiency gains brought by the enlarged verification window, of course. All right, so to fully verify and visualize the above trade-off dilemma, we conduct a comprehensive empirical analysis. The left group displays experimental results on the original default settings, while the right part presents our ParallelVLM perfectly balances window size and alignment consistency. So we first measured the actual forward inference latency of two mainstream vision language model suites, Lava 1 Vision's 7B, 72B pair, and Qianwen 2.5 VL 7B and 32B pair. So on the original configuration, their inherent speed ratio are only 5 and 3 respectively. When we set the video token pruning ratio up to 0.9, which means 90% of the video tokens are being pruned, the speed up ratio can be promoted to 9 and 5, which successfully enlarge the feasible parallel verification window. Apart from speed up ratio optimization, we further explore effective alignment enhancement strategy. We introduce feature guidance from the large target model to optimize the draft model. Well, traditional attention-based guidance suffers severe position bias, which we discovered. In detail, merely 4% positional weight corresponding to the first and the last 5 video frames capture over 21% total attention weights. Such uneven distribution severely damages the alignment stability, right? So therefore, we aim to design a brand new unbiased pruning guidance mechanism, right? So as visualized on the right slide, our ParallelVLM achieves optimal balance between the verification window scale and the cross-model alignment, even under high pruning ratio of 90%, reaching the best overall acceleration performance. Meanwhile, our pruning guidance strategy completely eliminates the harmful positional bias phenomena. So next, I will elaborate how our scheme realizes the above outstanding performance from 2 main designs. So the first design, we adopted optimized parallel speculative decoding pipeline, as I mentioned before. So we fully overlap the execution time of the draft model generation and the target model verification, so that we can completely eliminate the traditional mutual weighting overhead between the drafting and also the verification phase. So in terms of the verification window expansion, we perform adaptive token pruning on the draft model with adjustable pruning ratio alpha from 0 to 1. After lightweight pruning, the optimized verification window size would satisfy the approximate equivalence formula gamma equals the speed-up ratio C, which enlarges the parallel processing capacity. So third, for stable cross-model alignment, we propose a novel verifier guided token pruning strategy based on a cross-layer text-video feature verification matrix. So this design basically maintains a stable token acceptance rate tau under extremely high pruning ratio such as alpha equals to 90%. The interlayer difference calculation would isolate the interference brought by the positional decoding to similarity measurement, which would realize truly unbiased feature alignment. So we start our experimental verification by comparing our method with existing lossless video decoding acceleration approaches. So our baseline covers vanilla SD, SD adopt pure language-based draft models, tree-structured SD, and attention pruning-based Spec-VLM, which is a recently work published in EMNLP. So we set up 5 model combination with inherent speed ratio ranging from 1 to 5. So our method achieves 3 major improvements. So first, we successfully raised the optimal parallel verification window size of all these model combinations, improving the overall verification throughput by 1.7 times. All right, so in summary, we propose ParallelVLM in this work, which is an alignment-aware parallel speculative decoding framework. And it will efficiently accelerate video large vision language model decoding. Our solution perfectly fits long sequence video understanding scenarios and can be seamlessly deployed in real-world application. In the current era, with massive video data from industry production platforms and social media platforms, we hope that our work can provide a practical and efficient solution to lower the development and the deployment barriers and reduce operational maintenance costs for large-scale video understanding systems. So thank you all for your time to listen to our work. And if you have any questions, please feel free to reach out to us.